Here, the next example is next type of heterocyclic compounds are condensed heterocyclic compounds. This is also called as fused heterocyclic compounds. In the fused heterocyclic compounds, the suitable example is quinoline. In this quinoline, the two cyclic rings condensed are fused with each other. Here partly carbocyclic compound and another partly heterocyclic compounds may be combined with each other. Here, one of the benzene ring and another side it is pyridine ring. Pyridine ring, 5 carbon atoms and 4 one of the heteroatom that is nitrogen atom. Third pyridine ring and one of the benzene ring combined with each other that is to form a quinoline structure. Quinoline structure. When we compare with the quinoline, isoquinoline, in these two structures, atoms, the number of atoms are same. Bonding, pi bonds, number of pi bonds, all are same. But the difference is only place of heteroatom, place of nitrogen atom is different. In the quinoline, the nitrogen atom is at first place, but in isoquinoline, the place of heteroatom is second position. The remaining all same. Here, same pyridine ring and benzene ring combination. The position of heteroatom that is called second place is called isoquinone. These are the detailed structures and various examples of different 5-member, 6-member, 7-member and condensed heterocyclic compounds. Now we will go to one of the example of heterocyclic compound, that is pyro. Introduction to pyro. This is the pyrrole structure. Already we discussed in the nomenclature. 4 carbon atoms attached with the bonded with the one heteroatom, that is nitrogen. This is the clear structure of pyrrole. Here please observe 4 corners, 4 carbon atoms and one of the nitrogen atom. These 5 atoms in a plane, in a single plane. On nitrogen atom there is a unhybridized p orbital is present, but the difference is in this nitrogen atom unhybridized p orbital contains a pair of electrons, but the remaining all carbon atoms containing alone electrons, a single electrons, alone electrons. Only nitrogen atom, it contains a pair of electrons. This is the difference. Please observe, all of you, please observe. Now we will go to clear information, that is aromaticity of pyrrole. We'll discuss. Pyrrole. In the structure, we observe 4 carbon atoms in pyrrole, 4 corners, 4 carbon atoms are there. 4 carbon atoms attached with one heteroatom, that is nitrogen. That is nitrogen. All these four carbon atoms and one nitrogen atom undergoes sp2 hybridization. All these four carbon atoms and one of the nitrogen are in the same plane, but the, because that the total structure is planar, it makes a planar pyrrole ring structure. Is it clear? It's a planar structure. Each ring atom also contains unhybridized p orbitals. Please observe, all the carbon atoms contains an unhybridized p orbital. All carbon atoms unhybridized p orbital, and those carbon atoms contains alone electrons, a single electrons. Just now we observed a single electrons. Those p orbitals perpendicular to the plane of sigma bonds. Sigma bonds attached with the CC and CN sigma bonds are perpendicular to those unhybridized p orbitals of carbons. Is it clear, all of you? Now, here p orbitals are parallel to each other. P orbitals means that unhybridized p orbitals are parallel to each other, because that overlapping between p orbitals is possible. Overlapping means all those four carbon atoms unhybridized p orbitals and another nitrogen unhybridized p orbital. That nitrogen unhybridized p orbital carries a pair of electrons, but even though it undergoes overlapping. Five, what is it? Five orbitals. Five orbitals overlapping with each other to form a cyclic delocalized cyclic delocalized pi molecular orbital containing 6 electrons. This is the difference. 6 electrons means here the total number of non-bonding electrons are 6. In what way? 4 on 4 carbon atoms contains single electrons, alone electrons, and one of the nitrogen atom containing 2 electrons, 2 from one nitrogen, 4 of 4 carbons. The total number of non-bonding electrons are 6 electrons to form a delocalized cyclic pi molecular orbital. This is called as aromatic sextet. This is called as aromatic sextet, because that the resonance of these 6 electrons, it follows, it exhibits Huckel rho. Huckel rho. Finally, this pyrrole is purely aromatic. This pyrrole structure is purely aromatic. Is it clear, all of you? Is it clear? The last structure. Once again, please observe all the 4 corners, carbon atoms and alone single electrons. This nitrogen atom, it contains unhybridized p orbital, but pair of electron. Pair of electron. All these unhybridized p orbitals are undergoes overlapping with each other. Is it clear? Okay. Now let us go to properties of pyrrole. Properties of pyrrole. The first property, tautomerism. Pyrrole undergoes this special property, tautomerism property, because that the extra hydrogen atom bonded with the heteroatom, that hydrogen atom migrated with migrated on various places. After that migration, you will get a different structure. You will get a different structure. That is called tautomeric structure. Tautomeric structure. Here, please observe a rapid migration of hydrogen from nitrogen to the carbon. Various corners of carbons. This particular hydrogen may be shifted, may be migrated. We will observe how is it migration. Here, first structure 1H pyrrole. 1H pyrrole, it is the original structure. Original pyrrole structure. Original pyrrole structure, that hydrogen bonded with hetero atom and two pi bonds are there in the pyrrole structure. But when we observe second structure, what happened in the second structure means the hydrogen, first place of hydrogen atom is migrated, is shifted to third place, shifted to third place of carbon, because it is called as, it is named as 3H pyrrole. 3H pyrrole. It is one of the tautomer structure of pyrrole. It is one of the tautomer structure of pyrrole. Tautomer means one of the all the total number of atoms are same, number of bonds are same, but only one of the atom migrated or shifted to another place. It gives different structure. It gives different structure. Now let us go to last structure, that is named as 2H pyrrole. In 2H pyrrole, what happened? Same situation. The first uh, hydrogen, the original structure, when we compare with the original structure of pyrrole, hydrogen atom is migrated, shifted to second carbon, because it it gets 2H pyrrole. These are the tautomeric structure, possible contributing tautomeric structures of pyrrole. Is it clear, all of you? Is there any doubt? Okay. Now let us go to hydrogen bonding. Hydrogen bonding. Hydrogen atom in the pyrrole. Hydrogen atom attached or bonded with the heteroatom. That particular hydrogen weakly, partially, weakly bonded with a highly electronegative atom, that adjacent another pyrrole molecule, adjacent nitrogen. Here please observe, it is represented with a dotted line. It is not original bond, it is not original sigma bond, it is partially bonded with a hydrogen and a nitrogen. Hydrogen of this pyrrole partial attraction with another pyrrole heteroatom. Here also same. Here also same. Hydrogen of this particular pyrrole partially attraction with another pyrrole molecule, highly electronegativity of heteroatom. This is called as intramolecular hydrogen bonding. Intramolecular hydrogen bonding, because this formation of this hydrogen bonding, it raises boiling point values. It raises boiling point values. Here also, please observe, another type of hydrogen bonding is also possible in this pyro. Intramolecular hydrogen bonding, but NH between NH with pi electrons with another pyrrole ring, pi electrons. Pi electrons are here. Pi electrons attraction, partially attraction with hydrogen. Here another type of intramolecular hydrogen bonding. This is another physical property of pyrrole. Tomorrow we'll discuss another topic. Okay.